team here with us tonight. The floor is yours. I'll do a bit of intro later, but
Cool. So hi everyone, I'm Mamy. I'm leading the ZK engineering team at Taiko. So Taiko is a Type 1 zkEVM. You have all the marketing materials on the Taiko.xyz website. I'm not doing marketing, we have the marketing guy there. But one thing is often people feel overwhelmed about everything that's happening in ZK, and I just want to highlight that we have a newsletter called ZK-Rollup 9, done by an amazing person called Lisa, and it covers everything. Of course, it covers Taiko, it covers Ethereum, but it covers other blockchain like Celo. We have things about Starkware, the new research that's going on, ZK-Rollup, Espresso, Aleo, everything, basically. So it's your starting kit to ZK. Now, a bit more about me. In another life, I used to do machine learning and data science. You have a proof there on Kaggle, which is a data science competition website that I did 6 years ago, doing a starting kit on PyTorch with a gold medal to help everyone on board on machine learning. The reason why I'm talking about this is I see a lot of parallel between machine learning 6 years ago and ZK right now. I will try to cover the parallel and explain where I see things we can inspire ourselves on from machine learning to deliver better ZK, scalable ZK. So a bit more about myself. You have my GitHub here. I've been writing a deep learning framework from scratch called RMAnswer with 1.1 stars. Started 6 years ago when I found machine learning too slow. So I wanted to do a deep dive into how it's written. And similarly in cryptography, I write something called Constantine, which is a library for ZK primitives. And currently, for example, it's the fastest as multi-scalar multiplication. That's why I've seen a lot of parallel between both. So to get started, some of you, maybe many of you, have been struggling with ZK circuits. They have heard this term, this word being thrown around. And actually, in machine learning, when I started to learn how to implement machine learning, the first term I did was chapter 1, circuits. And we also had, like in ZK.
Can you zoom in a little bit? Zoom.
Let's see, zoom. Can we
yes,
zoom?
perfect.
Okay. Chapter 1, circuits, and we add addition and multiplication gate, just like in all ZK proof system right now. So this was 6 years ago in machine learning. It's today, it started a bit like 3-4 years ago, especially with Aztec in ZK. So when I learned machine learning, I did all of this, except that I didn't use JavaScript. I use a compile language and try to create an abstraction of top, which is where ZK is starting to go with many languages like Leo, Lurk, Noir. I have a whole list of 8 to 10. Cairo, of course, thanks to our Starkware friend.
Have you heard of Keylong?
No.
Keylong is it's relatively new. It's developed by one of our collaborators, a company called BTQ.
Okay.
Chenmu Cheng, I don't know if you're familiar with him. He's a
No.
researcher. Yeah.
So everyone is doing many languages. Turned out this also happened 5 years ago in machine learning, and there is only two winner today. And I think this is consolidation is likely what's going to happen. And to give some unfair advantage to the people listening to the talk, I will explain some of the salient points of the languages that won. So, going very fast, this was the most complex circuits in this tutorial, just addition plus multiplication, addition and then multiplication. The difference in ZK is that after that we get those proof that the computation happened correctly. Now, what was the issue with all of this? In machine learning, we had to write those circuits with something called macro layer, where we do all of this in a big, with lots of code, very similar to what's happening with L2 today. It's painful, it's very hard to debug, it's very hard to audit. Well, in machine learning, they don't care about auditing. It's all probabilistic, so if you have an error of 1%, you actually don't see it. Unless you do not detect images, recognize images also, compared to cryptography where if you have one error, it's very easy, everything blows up. So one of the issue was, let's see, the number of line of code that I had to write. I know what to show you, something called gradient halide. The number of lines of code to write just to create a neural network. So for example, this is a paper from I think 4 to 5 years ago, and you have a number of lines of code comparison between a very, very low level, very optimized neural network layer written in CUDA to go as fast as possible. This is what we have in L2 today. We want to use L2 so that we optimize the number of rows and of columns. So for those who did not write any circuits, those circuits are placed into some kind of 2D layout, like as a room, and you want to minimize the number of rows and of columns so that you have the smallest proof and also the smallest FFTs. I see a parallel with machine learning at the time. Then you had a high-level programming language, so this is PyTorch, 42 lines, except that it's much slower. It goes out of memory for 4 megapixel images that you analyze, while in CUDA it takes 2 seconds. From 1 megapixel images it took 1.4 seconds, while in CUDA it was 3 times faster. So I have not looked deeply into the state of ZK language right now, like Leo, Cairo, and all the others, but I think there is still a lot of optimization that are missing to switch from those high level to the low level. Now, we have this one called halide. It's 24 lines of code. This is, I think, just something called bilinear transformation. So it just goes through an image to zoom or unzoom. And somehow it's again about 20 times faster than the high level code, and still about 8 times faster than the low level one. How and why? They use compiler technology. So I think today it's especially RISC-0 that is doing MLIR and compiler optimization. They use compiler technology, and I see a parallel between, for example, register allocation, which is on a CPU, for example, not on a Mac, but on a classical PC, you have 16 registers, and you have only those 16 registers to do all your addition, subtraction, everything. And compiler needs to optimize how to use those 16 stuff. We have the same issue in ZK with optimizing 2D layouts. And this is what this is doing. And I think it's a very the languages that will win will be those with a very optimized compiler that allow very few code to be written to be even more efficient than the L2 solutions or everything written from scratch that we have today.
Have you seen the L2 Lib
Sorry?
from Axiom?
Yes. The founder of Axiom said that he will try to come at this event.
Oh,
yeah, he's in Paris, so you can discuss with him about this. But I've looked into it. For now, it's a monorepo of the L2 ZK from Ethereum Foundation PSC team, and they only have macro optimizations. So basically, they're doing this.
I thought that so L2 Lib it kind of figures out the dimensions of the table for you. So basically, you just have a selector polynomial and an a selector polynomial column and a device column, and then it somehow manages to. There's some way they like figure out how to have like multiple inputs to a particular polynomial, of course, but then it re-optimize it.
Okay, I think that's an interesting point. I actually didn't look that deep into. When I looked into the L2 lib, I was trying to optimize the pairing circuits because for Taiko, pairing are very important due to the L3 requirement. We released a testnet with L3 support just 3 days ago. So you can try L3 Taiko on L2 Taiko on top of Ethereum on the Sepolia testnet.
Nice. Check it out.
I'm just curious, like, what activation function are you using? Is it a ZK-friendly activation function?
I don't know. This is not. I'm just drawing a parallel between ZK and machine learning, but we don't do ZKML in Taiko.
Oh, okay, gotcha.
Okay. But
Sorry,
if you want to ask about activation function, there are the EZKL guys. They were around in one of the HackerHouse, maybe this one. And they were mentioning, they were using a very specific one. So conclusion, compiler technology. Make it easy to write high-level code. This is way easier to audit than this. And auditors are very expensive right now.
But so it means that potentially at one point the compiler gets so good that it's even better than a human being at writing very low level code, right?
Yes, so this is what's happening in machine learning, and I think this will happen in ZK, but strangely, this doesn't happen for raw cryptography. So if I look into my own repo for cryptographic low-level implementation, this is something I cover directly in the README. Let's see, performance compiler kvat. And if you go into this link, this is Goldbolt. So Goldbolt compile a line of so very huge privacy policy. This is a simple UIN 256 addition, so 256 bits, using an intrinsic called add with carry. And on GCC 9.2, so this is a bit old, I think it's 6 years old, this was what was produced, which is add, saving the carry, moving the data around in new register, doing a next add with carry, saving, etc. With Clong, or Clong, I don't know how people pronounce it, it just add with carry, add with carry, add with carry. And this is with an intrinsic. And the thing is, there are others, for example, for multiplication, where no compiler knows how to produce the optimal code, and the difference in performance is about 40%, which is one of the L2 curve.
Well, for ZKML, we're working with like something like FP16 or like in 8. We should be using something like percent time, right? So then we wouldn't be doing too many big integer operations.
Yeah. For ZKML, you don't do many big integer. And also, one thing I realized is that for example, while you have to resort to assembly for cryptography, for ML, you can use SIMD intrinsics,
Sure.
and they're really good at that. And actually,
It's still slower. It doesn't really make that much. Like you mean for vectorizing, like the individual small
so
operations?
actually no. There is the core operation on machine learning is called matrix multiplication.
Oh sure.
And there are people doing PhD upon PhD into accelerating this, and then tensor cores and other things. And there is a library called OpenBLAS that's about 70% assembly. So I look into a guy is called Shani. OpenBLAS is an optimized library that does matrix multiplication, and I think it's about those 16.6% of assembly. It's like 5,000 lines of code just for matrix multiplication. So let's look, I think x86 64-bit, and you have those very so it's called SGEM normally for a single so let's take Skylake X, which is the latest architecture.
Can you maybe zoom in a bit? Again?
That's fine. So this is basically what I was explaining in the code comparison. This is the low-level, very optimized code with register specific register allocation, and it's all assembly. It's impossible to audit. Like impossible. You have thousands of lines of code, and you have to keep this in mind. And in my one thing I didn't say is that I'm also a high performance computing enthusiast. So I wrote my own multi-threading library. I did a compiler using SIM intrinsics for matrix multiplication. It's in my benchmarks. And this compiler does what they do in 10 lines of code. So when I need to add a new SIM support, I just do those microkernel generator, IVX 512, and 13 lines of code, and you have something that is as efficient as those 2,000 lines of assembly that you've seen. And this is something that I hope on the ZK side we also get, like Rust macro, compiler
It's
with
like
AST.
a macro for inline assembly kind of a deal.
Exactly.
Very cool.
It's a macro for inline assembly. It's using the NIM programming language, which is Python with types. Basically, if I say that very rapidly. And I have some benchmark there where I'm over 20% faster than OpenBLAS in some of my PR, which is it was in let's see, I think it was this one. So you measure performance with gigaflop per second, and I reached 2.8 teraflops. The theoretical maximum was 4 teraflops, and as OpenBLAS was 2.7. It should be somewhere. Well, it's in one. I put benchmarks in all my PRs, so it's easy to follow. So yeah. Compiler.
Compiler.
Sorry?
Why is it so much better than the hand-coded one?
Well, most of the bottleneck right now on current CPU is not the number of operations that you do per cycle. A cycle is one, like if you have a 4 GHz CPU, a cycle is 1 divided by 4 billions. It's the memory. It's how fast you get data to be processed. And it's even worse with hyper-threading, because with hyper-threading, you have your hyper-threading, the whole reason it's used is because those CPU core can handle a lot of operations in parallel. We call that superscalar or instruction level parallelism. But getting data is too slow, and with hyper-threading, you have basically you want to get data for two different things, and they conflict with each other. They evict themselves from L1 and L2 cache. And if you want to see how complex the memory optimization I do on the machine learning side, and I have the same for my cryptographic accelerator, you can go into benchmark, matrix multiplication, and I do some, let's see, it's in common, and timing. I have some computation into how to keep data into register, then how to keep them into L1 cache, and how to keep them into L2 cache, resolving very area and of a rectangle plus perimeter, like very quick math. But it's kind of fun to do this. I have a similar approach for accelerating multiscalar multiplication.
Did you figure this out analytically, or did you have any experiments that
you have so I did experiments, but you have papers. It's all like in my code you have all the references, because otherwise when you go back 6 months later you just forget. And there are this one is a tutorial, so to learn how to implement high performance matrix multiplication for people who do ZKML. And then those three are about getting the last mile, and then my advantage is on the parallelization, multi-threading side. So a lot of people are using Rayon in Rust. It doesn't offer all the. There are three main parallelism paradigms. Rayon offers data parallelism. It's when you have data that you can process independently. Usually you use OpenMP with for loop. There are two others. One is called task parallelism. This is basically what Go does, or even async Rust with Tokyo. You launch a task, and at one point you await it, and you get a result at that point. This is something I use. And there is also something called data flow parallelism or stream parallelism, or it has 6 different names depending on the research you are reading. And this is more event-based, and this is an advanced programming model in OpenCL and CUDA, where you say when this is ready, trigger this other part of the computation. And if you mix all of those, you can reduce latency as much as possible, and you can do something called latency hiding, where once some data is not ready, you make progress on something else. This is, for example, extremely useful for multiscalar multiplication when you do a reduction of all the things you study in parallel.
Have you done any benchmarks with trying to actually use these strategies in prover?
Not in a full prover, only in multiscalar multiplication.
But the idea should carry over.
Yeah. especially if you can start, for example, in the generating the proof, you might be able to generate some proofs in parallel, while not having to do those, I don't know.
Because there's like extra operations that are being done that might make like some of your like caching like strategies not work.
Yeah, so there are some extra
Or
operations,
different,
but the scale, the magnitude is like 1,000 compared to cryptographic operations, so it's a very low overhead. And if you want to finish on the multi-scalar multiplication benchmarks, it was a couple of months ago.
Can you zoom in again a bit?
Yeah.
Thanks.
So I was trying to tune a multi-scalar multiplication on my machine, which was 18 cores Skylake X CPU, and I benchmark against NARC. I found a bug, a performance bug on their site, tagged the team. So NARC is from Linear. From Blast, which is sponsored by Falcon and the Ethereum Foundation. I'm 2.4x faster. Most of it is due to those memory optimizations. And benchmark against Bellman, 35% faster. Barentenberg from Aztec, 25% faster. And a couple others in others, and I plan to. I have a detailed issue on how to port those to PSC team, L2 ZK. So if you want to know how to reach the same order of magnitude of performance, you have those 6 steps. Yeah.
Is that like already a PR or is it there still?
It's an
work to be done?
issue, and people in the team are working to make this, but it's implemented in my own NIM repo, and now we need to convert this to L2 ZK. So estimated improvement, conservative is, I think, I don't know, 3x, 2 to 3x, I think. Well, but there is already assembly optimization that improved perf by 35%. That was already merged a month ago. But compiler.
Yeah.
And then next up, we also have Carter from.
Hello everyone. Yeah.
Do you want to do some showcasing, or we could just like?
Yeah, I don't really have anything